So, guys, welcome back to the day two of Rack to Riches, this mini course of 2 days. I'll just very quickly recap what we learned yesterday. We learned that there's such a thing as retrieval or the search engine, which comes broadly in two variants. The keyword search, which is based on the concept of inverted index, and it's a form of associative memory. Then we took these examples of four documents, but in your mind, when you see four, think 4 million, right? And lots of that. But the concept ju- uh, scales up with it. We call it inverted index, sparse index, and so forth. These are all keyword search indices. Relevance is detected, and we didn't cover the topic of relevance because it gets a little bit more sophisticated. And there are well-established algorithms like BM25 and so on and so forth. But we'll keep that for the real course. We said that the language is infested with a lot of ambiguities um, and need for interpretation. It has homonyms and polysemy. Language also has other problems. One of the big problems is when we talk, quite often, we don't know in a conversation what does it refer to. Right? Sometimes you're listening to people and they have been going on and then say, as you can clearly see it, and then you wonder what was it, right? And then you hear that X talked to Y, and while Y was saying this, then something happened, and then he did this. And you're wondering, was it X or Y? Does it happen to us, guys? It's pretty common. So, quite often, you need the context, really understand the context to know what is being referred to by it and he and so forth, or she and so forth, right? So, the word bank we took as an illustration as having multiple meanings. And we realized that quite often, some of the meaning of the word is in the word. The rest of the meaning gets clarified in the context. Sometimes all the meaning is in the context. The context clarifies the meaning. So, for example, if you were to say, I went to Wells Fargo to deposit my check, the word Wells Fargo, the phrase Wells Fargo, immediately rings as semantically a bank. Are we together? Right? That is that. We talked about attention. What is attention? In simple terms, attention is given many inputs that are coming at you, differentially how much weightage you put at each of the inputs. And context decides that. We took the example of hiking. If you're hiking and there is no danger, you're enjoying nature's beauty. Your context is the purpose of hiking was to appreciate nature and exercise. On the other hand, if you hear a growl from the bushes, that context changes immediately. Survival is the context, and your attention moves completely to the bushes. Right? You're looking for the predator in the bushes. So that is the concept of attention. We talked about the concept of a language model, a sequence to sequence models, and the concept of language model. Language model is the modeling of the input as thing, and more broadly, the neural network that's capable of doing it. A neural network that's capable of capturing or understanding language in simple terms, or more specifically, doing as lossless semantic capture as possible of the text. How we do it is a long story. How can you take, if you really think about it, we take, metaphorically speaking, a bucket of sand from the desert, do all sorts of alchemy to it, and at the end of it, we end up with this machine that understands human language. Isn't that one of the greatest wonders in the world, that it happens at all? That it can understand human language with all its nuances and complexities. But it does happen. We talked a little bit about the landmark paper, Attention is All You Need, and how it started out as a CargoNet paper. We talked about distances, concepts of distances, and how Euclidean distance breaks down in higher dimensional spaces because everything is far from everything else. Right? And it's not really helpful. One close analogy is Wyoming versus Bay Area. Bay Area neighbors are neighbors. You stretch your hand out of the window and you can knock on their window. In Wyoming, a neighbor in quotes is 1 hour drive away. Right? So neighborhoods don't make sense in a Euclidean sense, but they do still make sense from a angular sense. Right? From an angular sense, you can still, and you do that angular distance all the time. When you look at stars and you said, look at the belt of Orion, turn left at that belt, right? And then move down and you'll see Sirius, for example. We navigate the stars in our mind using that. That is looking at the angular distance. I finally end with a touch of sort of higher dimensional geometry by saying one of the lesser known facts, actually, that the reason semantic search works at all is because of a deeper mathematical fact, which is called the concentration of measures. It means that in certain high dimensions, all the random vectors will be far off from you. They'll be on the equatorial plane. If you're sitting at the North Pole, they'll all be along the equatorial plane. And if something happens to be near you, proximal to you, the only valid explanation is it is semantically very similar to you. Are we making sense? Right? It is a point that represents semantically something that is very similar to what you are. So that is what makes AI search possible at all. Right? It gives you a good resolution, very good accuracy. Now, there are two perspectives on RAG. Perspective one was, we have been doing search. Now that there are language models that can understand, why not complete the journey? Why give users the search results? Give the search results to an LLM and let it answer the user's question fully. Another perspective is LLMs tend to hallucinate. They tend to answer things from the parametric memory, but you want it to answer from a corpus of documents. Or the LLM can be dated. It has a staleness factor, hallucination factor. Much of it you can mitigate by augmenting it with a search system. And the search is based on your document. Most of the corporate knowledge is proprietary. Your company won't reveal. Imagine you're Boeing. You wouldn't talk about your wingspan design. You wouldn't talk about the material science of your turbines, right? Jet turbines. But those things are there in your documentation internally, and you do want it to be available as a feature to your internal employees and accessible the way people use ChatGPT to find public information or get answers from public. So that's the other aspect of RAG. So that was what it was yesterday. Today, what I would like to do is do it through code. So we will do it through code. Now, I must also mention that all the code is here. Let me just write it. If you go to Support Vector's website, if you go to GitHub, I believe the project is called, I've forgotten the name, Rag to Riches. Is it with underscore or with underscore, right? Yes, Rag to
Underscores.
Riches. If you're here, please don't try to clone it now, clone it later, because it's a big project, 2 gigs. It's a self-contained project. The moment you download it, you can just run with it. The whole code is under permissive license. You can do with it everything except one thing. Can you guess what is that one thing? Come again? Oh, commercial use by all means. Lots of generations of people have used that project in their company. By all means, go incorporate it, call it your own. But there is one thing you cannot do. You can go ahead and call it your own. One thing you cannot do. Can you guess what? Sue us. Don't sue us for that code. That's the only request we have, right? Use it for whatever you want, but if you get into trouble, don't come back and sue us. We are pretty sure that code is harmless and it is very well tested. Nevertheless, with that disclaimer, it is yours, right? and with no strings attached. And many people have used it as a starter code for their internal projects. So by all means, do that in your companies. No restrictions for commercial use. Now, what I would like to do with that is begin with the topic. Let's think through the RAG journey, and then we'll walk through the code. Suppose you have a corpus. We use the word corpus. What in the world could we mean by corpus? Corpus is the set of documents, right? The collection of documents. What do we mean by document? What do we mean by document? It could be a word, sentence, para, chapter, or actual text of a document, text of whole docs. What else could we mean by document? Image, and video, right? It could also mean MRI, exactly, code. And nowadays, more generally, we also mean data that is in structured form, tables, rows of data, everything. The word document in our field is pretty broad. It encompasses all of that. Now you say, well, if I want to look at data that's in a tabular form, uh, shouldn't I be using SQL? For example, if it is in a relational database, shouldn't I be using SQL? And the answer to that is yes, you can. And in fact, under the tent of RAG is pretty big tent, and many things live under the tent. One of the things that lives under the tent is text to, like, user query, natural language a question automatically converted into a SQL query. Okay? So when you, for example, take our course, Enterprise RAG, one of the big themes you do learn about is how to do good quality text to SQL generation. And that too is part of RAG. So how do you access tabular data? You don't want to treat it as just keyword or words or things like that. So everything is part of this RAG document thing. So we have a corpus of document, but for today, we will start with something simple. We will start with, let's say, words and images. Is that reasonable? Right? And what's the journey? What's the journey of a document? So what happens is, the first thing is, if the document is too big, do you want to create, so think about this way. I will call it a doc, an embedder. The first thing we need is an embedder. That will do what? I'll call it phi, right? And let's say that this converts it into a vector. A vector, should we call that vector vi? Let's call this document xi, coming from this. This is equal to the phi of xi. Is this notation reasonably clear, guys? All I'm saying is the phi is the embedder that, given a document, produces a vector. While we keep using the word vector everywhere, more strictly, it is a point on the sphere, right? And this nuance is only for those on the off chance that some deep geometers are sitting in the class with PhD in information geometry. They would say, well, you have to be strictly right, but we'll deliberately not be strictly right. We'll just say vector, right? Otherwise, we'll have to rename all the vector databases as point on a manifold databases, and we don't want to do that. Right? So vectors. Now, questions can be vectors. A user says, can you describe for me, right, what do cows do when they're happy? That text has a semantic load. The semantic content of that text query is, and let's be very clear. While we are putting points on a sphere, I'll just represent it as this. What is happening is, suppose you have a point x1, x2, xn. They become points here, v1, v2, vk, vn. Isn't that? Let's say the proximity of 2 points, what is it implying? In a semantic system, what is it implying? A language model will put, when will it put 2 points together? If they are semantically similar. So let us say that I have a query, a new query comes, Q comes, what do happy cows do? And that query happens to become a vector here. Can you tell what should be which of these, your search result, what should be the first 2 search results? V1 and V2. And what documents do they correspond to? X1 and X2. So what you will do is, you're basically going to vector database to figure out which points are close, and then looking up their ID. The vector database will tell you that's the ID of that doc. Then you go back to the doc and read it up, and you show that as search results. Isn't it? And sure enough, it will say the happy cow something like this, right? Or the cow happily in the meadow. And sure enough, they look quite relevant. Are we together? So that is the heart of it. The journey is convert the vector, convert the query. So what will you do? The query needs to first become VQ. VQ also goes through the same embedder, isn't it? Now VQ has associated with it, the vector database remembers so when you give this, let me just do this. Let me write it correctly. The step 1, you do this, step 1. What is step 2? K nearest neighbor search in vector space that the vector database will do. Actually, it is approx K nearest neighbor search. It's one of the little facts that you learn, that to do exact search is horrendously expensive. But to do a search in which in practice you don't lose any accuracy, but theoretically you do, is lightning fast. Systems like FAS and implementations in modern vector databases like QDrint, etc. So to give you a scope of how fast approximate K nearest neighbor search works in real terms, think of a internet property, a social media property like Facebook's Meta. What will you take? Instagram, right? Or Snap, or I don't know, YouTube, whatever it is. Suppose you have 100 billion images and pieces of text. Let's take just images for simplicity. You do a query, and you may be doing a query, may be either a text or an image, it doesn't matter, and you're looking for nearest neighbor search. In modern vector databases with modern algorithms, 100 billion. So just to put it in perspective, if you have 100 billion rows in a relational database, how long will it take for a query, a SQL query, to return? Even on the most powerful relational databases, how long will it take? Assuming that you haven't put indices, it's a flat table. Couple of hours, isn't it? Right? So guys, and this is one of the underappreciated things. Do you realize how long a vector database takes in production? Make a guess. 10 seconds, 20 seconds, 1 minute. Yeah. Typically, the total budget, including the network traffic, right, is capped at 30 milliseconds or so. Otherwise, actually pager alerts can go off in some systems, right? That the queries are returning too slow. Think about it, 30 milliseconds. And that is when you are taking at least a few hundred queries in parallel, concurrently, right? So in these systems, how do you just think about it this way? You can't even believe that it can be done, isn't it? You have just shifted through 100 billion items and found the nearest neighbor item in milliseconds and come back with it. That's one of the, isn't it absolutely marvelous that you can actually do it? We will, I mean, of course, that's in practice when we take people through the whole exercise, then it sinks into them how powerful these beasts have become for enterprise scale work. Right? And especially enterprise is nowhere compared to web scale. So when you do it for enterprise documents, most things will return in single digit milliseconds. Right? Rapidly they return. Anyway, so you do the k nearest neighbor search. What is step number 3? It returns IDs. ID 1, ID 2. What is it returning the ID of? Actually, every search result is like this. It returns ID and similarity score. Similarity score 1, ID 2, sim score 2. Similarity score means how close you are to the query. Right? Does that make sense, guys? Right? So think about this. What is a good measure of similarity score? If this is the angle theta, a very obvious measure of similarity is cosine theta, isn't it? If these 2 points are sitting on top of each other, angle is 0. What is the cosine of 0? 1. Extremely similar. If on the other hand, it is sitting at the other end of the polar antipodal point, what's the similarity score? -1. Right? It's the opposite. So the range is completely dissimilar to completely similar. But most similarity scores are not -1, they're closer to 0. Remember, what did I say? Given a query, all the random vectors will be where? 90 degrees on the equatorial plane. Right? If you take that point as the North Pole, everything will be at the equatorial plane respect to it. Or rather, equatorial region will be where they'll be located. So what is the logical step 3 therefore? Look up ID 1, ID 2, wherever you have relational database or wherever MongoDB, wherever you have kept those. Now you have the row IDs, right? And return to user. But that is only the retrieval part. User asked a question, but except that in a RAG system, you don't return it to user. Just a retrieval. A search engine would return it to user, would show you the search results. But what is the RAG journey? You instead hand it over to the LLM. And you say the LLM, here is the user query, here is the relevant documents. Can you please understand these documents and answer the user query? That's a journey, isn't it? So let us write down this journey and then walk through the code. Given a user, so there are 2 things. First, you have to build the index. Build your vector database. So let us look at the indexing part. In the industry, we call it indexing. This is what you do when you have the luxury of time. Documents keep pouring in. What will you do with each of the documents? Remember, our notion of documents is, it could be anything. It always reminds me of Humpty Dumpty in Alice in Wonderland. When Alice asks, what do you mean? Humpty Dumpty says, a word means exactly what I want it to mean. Document in our field is like that. It can mean anything that people want it to mean. So xi, any document, new document that comes, you can apply embedding to create a vector. V is equal to phi of xi. Where do? You insert it into your vector DB, isn't it? So your vector DB is populated. One conceptual way of thinking is, imagine, so here is one way. How do you think of, by the way, how do you visualize 1,000 dimensions? How do you visualize 1,000 dimensions? How many of you can visualize 4 dimensions? So can you visualize 2 dimensions? Easy, right? 3 dimensions, yes, getting harder. So when I came to grad school, at that time, people were in my department, they were doing things like superstring theory. And they were happily talking and saying, as is obvious in 11 dimension. To me, it was not obvious at all, right? I couldn't see 11 dimensions, far from being obvious. Then they would talk of 4 dimensions because it turns out that space-time makes it 4 dimensions. That also I was having tough time grasping. Math I could see, but I couldn't visualize it. And it wasn't obvious at all till somebody told me a trick. He said that, see, always think on a page. 2 dimensions is easy to think, right? Think in a page. Once you can visualize in a page, loudly say, as is obvious in 1,000 dimensions. Right? So that's what most people do. Right? Except that you have to be careful. Higher dimensional, as we talked about, they have weird geometry. They have the curse of dimensionality, concentration of measures. They have very interesting geometry that we are only now beginning to understand. But so long as mathematically you can see that you are safe, loudly you can say, as is obvious in 1,000 dimensions. But you always put it in 2 dimensions. So you see, I made this picture in 2 dimensions, isn't it? So a vector database is nothing but visualizable of points as universe is certainly not in 3 dimensions. Universe is in 4 dimensions, space and time, minimum. And if you believe the superstring theorist, the string theorist, it is in 11 dimensions. So you say, where have the rest of the dimensions gone? They say, well, you mere mortals can't see it. It's compactified in a very tight bundle up loop and kept away from you. If you, those of you who are interested, look up, guys, one of you have your audio on, please. Yeah. So if you really want to see what I'm talking about, look at Calabi-Yau manifolds. You'll know what I'm talking about. So they're very interesting theories people have. But indexing. So what does indexing mean, looking at this picture? Populating this page with lots of dots, where each document is a dot. You're done with indexing. You have 100 billion dots sitting on this page then. Right? Now what will happen with those dots? There's something very interesting about the dots. They'll form clusters, they'll form patterns, they'll have things. All the topics that are related to RAG will be in one little, like a city on the map, right? Concentrated at one place. Other topics will be concentrated, located somewhere else. They will all have found a place under the sun, or rather a place on the page, isn't it? A meaningful place on the page. Now, when a query comes, then comes the part about inference time. Oh, my hand is, why is this jumping around? Okay, inference time. Inference time, what comes? A query comes. The query also needs to be converted by the embedder into a, what were the 3 steps? First, convert it to a vector, do k nearest neighbor search, and then get the ID. So let's do that. First thing, it will become VQ. VQ would be phi of query. That will land, let's say, here. What are the k nearest neighbors? Let's make a little neighborhood here. We got a few points in our net. We cast a net around it. We got a few points in the net. What do we need to do now? What's the second step? We look up the IDs. And when we look up the IDs, we retrieve the documents. Once we retrieve the documents, what do? The search part is over. Vector database is returning you the IDs. You take the ID, go to your auxiliary database where you actually kept the documents, and now you're ready. What will you do with that? You pass it on to the LLM. But what will the LLM know? What will LLM say? What is this? This list of results. You need to do this. You need a prompt at that moment, right? You need a system prompt, an instruction prompt, which will say this. You are given a user query in the simplest form and a list of facts retrieved as search results. You answer the user query using only and only the facts in the search result. That's a very naive way of putting it. Actually, it doesn't quite work, but conceptually, it is what you want. Then in the prompt, you give a placeholder for query search result. So now to the LLM, what are you giving? You are giving it the instruction prompt, and you're giving it the user query, and let me put the word user just to be clear, and you're giving it the search result as one giant text input. LLM will do what it will do, right? It might listen to you, it might misbehave, but depends, right? And the output of that is your search result, the naive output of that. But of course, that output may not be grounded in facts. So there are lots of dangers, but today we'll keep life very simple and we'll follow this two-step process. So our two-step process is how does it look to the external world? To the external world, from a functional point of view, query goes in first to the retrieval system. And so in our code, we'll inspect that, search, and out of it comes results, top tier results, right? Which along with the user query and with the instruction prompt, together goes into the LLM to produce response. This is the most naive RAG that you can build. Do we agree, guys? This is it. So today, we are going to go into this journey, step by step. And now, is this a good review of what we talked about yesterday? Right? So let's go into code now. As I said, the code is all available on GitHub. The GitHub location is, did I share that? Yeah, GitHub, supportvectors.com, rag to riches. Don't download it now. It's a huge download. Do it later. And again, do whatever you want to do with it. Just don't sue us for it. Now, let's go back and look at the code. Is there a way to get rid of this also? No. A way to get rid of cloud code. Too many things these days. Okay. Let's carefully walk through the code. We will talk about, oh, by the way, do I need to recap what is wrong with naive RAG? Yesterday I showed you an example. Could one of you recall what that example was? That's right. we give it only document Greek civilization and asked it a question about Greek, it answered. But when we asked it about Chinese civilization or Indian civilization or any other civilization, it happily answered. It shouldn't have. It has shouldn't technically have knowledge of that. I mean, it's not there. It came from the parametric memory, right? And a very practical example is you're trying to sell your products and your customer service RAG application helpfully directs traffic to your competitor. It actually happened, right? You don't want that. So let's go and look at what we have here. And this code base, guys, again, I'll just walk you through. Read it at your leisure. Let's look at the types and see if it makes sense. So first is distance metric. Like I told you, Euclidean is not very useful. I've given you this choice. Which is the distance metric you should, I mean, the one that I almost always use, cosine. Now, here is the thing. If your distances are all on a unit sphere, unit hypersphere, as I advocate, then Euclidean and cosine become more or less the same thing. Are we together? You realize that if they are on a unit hypersphere, you are moving along the arc. The distance you move along the arc and the angle between them are related. So then it doesn't matter which one you are using, right? So cosine is the one. Vector record. What in the world could be a vector record, guys? It is something that you put in the vector DB. It will contain 3 parts. This is important. The attributes are 3 parts. It is, I think I should open the outline to make it obvious. Open view outline. Okay. And more. Guys, I can, but what it will do is make it a little hard for me to scroll up and down. So I would advise join the Zoom. Okay. So look at this. Vector, it contains an ID. Why do we need an ID for a vector record? How will we know which record to go in the actual source of truth documents database? The vector itself that will be needed for the vector DB to do the math, k nearest neighbor search. Make sense? And what is the other? Metadata. Metadata is very useful. What could I use the metadata for? Metadata is any key value pairs. It's an auxiliary database. You can use it for filtering. So here's an example. Suppose the query clearly says, when we are talking of bears, look in financial news, not in general news, because the word bear, right, has, and bull, they have entirely different meaning in Wall Street than in common language, right? So you want to filter down the results by some metadata, right? And here is a trick that you can use, a cheat trick. When you're just playing around, an easy way or a good thing to do is, without, if you don't want to go back to the another database to pick up the row that contains the text, what you can do, most vector databases, you can give the actual text in the metadata, right? So you created the embedding vector, but nothing prevents you from storing the text right there. Is it making sense, guys? Right? So for text, you have a cheat way. You can just store it right there. So that is why you need these 3 fields. A vector config, model config means what could the model config have? Which embedder you are using. It turns out that there are many good embedders, and just when you found a good embedder, a better one comes out. Right? So then you start having bias removes, and you want to re-index all of your documents with a better embedder. More realistically, this is what happens, guys. You'll learn. General purpose embedders that you download, They're just a starting point. You are in a specific domain, right? Your domain could be hardware, networking, medical, right? Security, pharma, aerospace. So what you do is you don't just use a general purpose embedded. And in reality, whatever you download is a starting point. You fine tune that model on your data to, to perform excellent retrieval. The single biggest factor that improves a rack system at this point, assuming that your data is good, is the quality of the embedder. You fine tune the embedder. Take a very good embedder, whichever one you like on the internet. Download it, then own it by fine tuning it and creating your own embedding model. Right? So this is where you keep the embedding config. Convert to NumPy is just a helper. If the vector is not as a NumPy, you convert it to NumPy. Now you may say, hey, why NumPy? NumPy is not, for those of you who are hardware aware, you may say, hey, why NumPy? NumPy is not optimized for GPUs, isn't it? If you really want to search 100 billion points in milliseconds, you can't do it on CPUs. CPUs is not accelerated computing. The GPUs are literally thousands and thousands of times faster than a CPU. And the answer to that is, you may be tempted to say, let's keep it as PyTorch, torch vectors, torch arrays, torch tensors. That is optimized. But don't do that. The reason for that is almost all data vector DBs, vendors, they create their own optimized formats, right? GPU optimized formats for the vectors. And the lingua franca there is, the common language that they all like to speak is, give us a NumPy array and we will translate it to our internal vector representation, optimize, the GPU optimized representation. That is why preferably just give it as NumPy. It's one of the subtle facts you learn. Now, so that would be, the document becomes vector, it goes into the, go ahead. No. It is just the text converted or image converted to vector. That's it. Right? So, see, the vector record has ID, the vector itself has NumPy, and the metadata, where you can store all of this additional information. Now, let's think of search results. When I think of this, if there is one thing that I want you to take away, most of the time when people create RAG, guess what the output is? At the end of RAG, what is the output? Just text. Right? But you'll see that I would dissuade you from doing it. The first lesson is, don't do that. Do something better. But we'll go systematically. The first journey is the search engine, the retrieval system. It needs to produce search results. What will the search results contain? Each search result will have an ID and a vector and a metadata, isn't it? Common sense, right? It will return vector records. Then, so those are the bulk operation results, will return many, collection config. We won't look into that. Now, I would like us to see one more thing. Let's look at it as a black box and say text goes in, a vector comes out. Who is the guy doing it? An embedder. Does it make sense, guys? We need, first things first, we need an embedder. Right? So where is the embedder? Let's go into source, SRC, vectors, adapters. By the way, I must tell you this thing. There are many vector databases. FAS is one, ChromaDB is another, Qdren. FAS is not a vector database, but it's a library out of which you can home grow your own vector database. It's FAISS. Can you deconstruct the acronym? What could it mean? Facebook AI semantic search, right? That's that. Qdrant is very popular. We love it. ChromaDB is another very popular. We really like it. Then this is that adapters. Errors. It's always a good idea to have your error classes in place. And let's go. Let's go with that. PyTorch. What am I missing here? Is there anything that I missed? Base, factory. You keep factories just to say which database you are going to store it in. It's always good idea, because what will happen is, just when you standardize on X, your architects will leave the company, a new architect will come, and what will be the first thing he'll say? I don't like your vector database. This is better. Change over to that. So you want to decouple dependencies by separating it out. And that is what we are doing here. So that's vector database. So anyway, here I'm just keeping to vector database. But now let's go to the full RAG project. In the full RAG project, let's look at what we want to talk about. What's our data? First, we have to start with some data, right? What will be our data? I've taken a simple data. How many rows are there? 100. 100 rows of data, just so that you can play with it and read it. When you see 100, what should you say loudly? 100 billion, right? So think 100 billion, see 100. So imagine a lot of data, right? So by the way, this data is all animals are equal, but some animals are more equal than others. It's from George Orwell's book and so forth. So that is that. This is the data we will consider. So what will happen? Each text, each row is one document, right? These documents are rather short. I deliberately kept it short so that we don't deal with complications like chunking and other things for this particular thing. And we even have an image collection. And our image collection is vast. It contains 2 images, right? A car and a dog, right? But you should think 2 million. Lots of images. So that's the reason is that, we start simply. We'll build the concepts all in place. Qdrant is a database that we will use. Now, at the end of it, how should the, again, view, open view, outline. I don't know why outline is not the default. So if you look at an example of what we have given here, let's look through an example. We will assume that all the animal codes have been created into vectors and put into a vector database, right? So let's do that. How would we do that? We will first go and instantiate a vector database. You need a vector database, right? And then what do you need? Vector database is here. You need an embedder. Right? What will the embedder do? Take a text and convert it to a point in a vector. So you have an embedder. And where is the text? We already saw it in the JSON file, right? So we load it and load the animal. If the JSON, otherwise, what we do is we can recreate the collection. This is the indexing part. We can go index all of those points into the vector database. Simple example. And then there is some metadata associated with it. Just to show you the use of metadata, we added some basic metadata to it. What was the metadata that we added? Let's go back and look at it. It turns out we had some metadata. One of the metadata was author, other metadata was category. So we associated 2 metadata with the record, author and category, because then we can filter by that, if we so choose. Let's go and look what an embedder looks like. So text only search, vector DB, embedder. What should be the signature of an embedder? It should be the method. It should be this. You give it, uh, look at the signature of the method embedder. What should it be willing to take? An image in this particular case, or a string, right? So in this particular simple example, code base that I gave, I did not consider other formats. What have I not considered? Audio file, video file, DICOM, MRI images, and many, many other things. I've limited it to just image and string, text and string, just for simplicity. Because without loss of generality, we can explain all the concepts. Then, what should the embedding model return? It should return a point structure, which is basically vector with its this. Now, there are two kinds of embedders you need: simple text embedder or image embedder, multimodal embedder that can embed anything. Let's look at a simple text embedder. What will the simple text? So, what should the simple text embedder look like? How do you initialize it? The embedder, behind the embedder, let me go through this slowly. Behind the embedder will be a real language model, isn't it? You need to load a language model that understands that text and makes it into a point, converts it to machinese, to a vector. Right? So where do we get that language model from? For simplicity here, we just download it from the internet, a very simple model. It's called All Mini LM, right? It's just, as the word mini suggests, a small model. The reason we use this model is not because it's a very good model, but it is good enough to run on a laptop, small enough to run on laptop, and within the scope of a limited laptop, it's good enough, right? So let's read this code a little bit carefully. What is it trying to say? It is saying the text needs to be broken up into tokens, words, you need it, and etc., etc., because it turns out that there's a bit of machinery involved. We won't go into it. But at the end of it, you give it to the model to convert it into an output. At the end of it, what this thing will return is embed will return for you a point, a vector. Remember, point on the in the vector space. So embedder is easy to understand, guys. Who will use the embedder? The vector DB, embedded vector DB. What is the signature of the embedding vector DB? All vector databases, what do? Create, read, update, delete. Right? Isn't it, guys? CRUD operations. So you would create points. You would want to know how many points are there, search for points, delete a point. You don't actually update, you upsert. Like you say that, okay, here's a point. If the ID matches, forget about the previous point. Replace it with this. Right? Why would you do upsert? Because what may happen is the row, wherever your document is there, ID may remain the same, but somebody may have edited the text or the image. So you want to do an upsert operation. So far, so good, guys? Yeah. So that's a very good question, actually. Multimodality refers to the fact that you have different modalities, image, text, etc. But within text itself, there are many languages. So these days, so the history is this. Early embedders were very heavily focused on what are called resource-rich languages, like English being the prime example, yeah, French, and so forth. Over time, and so you can have an embedder which is very good for English, but gradually, and then people created multilingual embedders that could do many languages together. And those, in the early days, those embedders were significantly inferior to single language embedders. Right? So if you had content in multiple languages, you were at a slight handicap. Lot of research has happened in the last 2-3 years, and progress has happened. So that multilingual embedders have nearly achieved parity with single language embedders. And there has been projects or efforts, like for example, Meta's effort, Facebook's effort, called No Language Left Behind. So these modern embedders can handle up to 200 languages. Right? No, they directly embed. It turns out that, see, that imagine a translator who can understand 200 languages, but whose private language is still Tamil, right? Listens to it and immediately, oh, this is what the users, this is what I heard. In the same way, these multilingual embedders, they can understand, they can hear or get input in so many languages, but it still writes its private notes in machinese, means directly converts it to vectors. That's a mental model you should carry with you. They're very good. So silently, it's very interesting. While we think that these things are easy, none of these things have been easy. And each of these pieces in the rack system is going through rapid research and evolution. Every piece of it is like cars. If you think about it, Ford made the car in what, 1910 or something like that, long, long ago. I don't know the exact date. It, Yet, over 125 years later, the cars of today look vastly different from Ford's car, isn't it? What has happened? Slowly, every component of the car has been evolving, right? And RAG is like that. It's a complex piece of machinery, and people have been innovating in each component of the machinery, including multilingual embedders. And rapid research is happening there. So I hope that answers your question. So what is the vector database going to do? Like, the most important function that it will have is search for points. But how will you give it a point? Vector database doesn't know that you're doing RAG. It says, give me, vector databases are neutral. They say, give me a vector and I'll give you the nearest neighboring vectors. So the query also needs to be translated into vector. Who will do the translation of query into vector? Now you're getting you see the pieces come together. Right? This is it. So now let's look at what the search system should look like. What will the semantic search look like? Well, semantic search, amongst other things, should contain a method, let's say search with image or search with text. Let's look at search with text. It's more intuitive and easy to understand. When you search with text, what will go in? Text will go in and search results will come out. Does that make sense, guys? Queries will come out, right? So let's look at an example of search. By the way, if you want to see examples of how to use it, all of those examples are here. Usage examples are all here. Go and run the usage examples. Right? Oh, right. Example with RAG with elements example. So that's the best way, because the code base is a bit large in the beginning. It may look intimidating. Those of you who know how to put breakpoints in code and step through the code, you are at an advantage, because you can put a breakpoint in the which code, which is the starting place, the examples, the main methods in the examples. Put a breakpoint there, stop the execution, and step by step drill down into the code base and see its execution. Multimodal search is also like that. You can give it, for example, an image. And so now multimodal gets interesting. You can give it an image and search the entire vector database, and it will return text as well as image. You could give it a text and get again a combination of that. And I would like to show you all of these. But before that, let's just go through one example and see if it runs. I hope it does. Okay. What are we doing here? Just for your fun, the main class, the outer, the thing that is the whole RAG, I've simplified the name of that as the animals class. So if you really want to say where do all the pieces come together, the retriever, the LLM, the prompt, where will you look for? The animals class. Are we together? Why did it go here and not up? I don't know why it did that. Animal. Let me see if I can do. Oh, still opened here. I think this UI is going through, cursor is going through rapid evolution. And good. Again, it just opened it here. Drag it up. Huh? Yeah, I just updated cursor and I have to get now used to this. Uh, open in chat. Why would I open it in chat? Okay. All right, we can directly go to the end. So here is the end. So just for you to know, I've simplified everything to one function, outermost function, rag, animals.rag. This is your entry point. Are we together? All you have to do is give it your input query. It will do the search in the vector database, pass the results to the LLM, and get you the response. Now, I do want you to pay attention to what it produces. If you look at RAG with examples, let's run this. Let's see. Oh my, I'll just get rid of this. As many windows as possible so we can pay attention to this. Let's look at what happened. We gave it a formatted search results. What were we doing? Let's look at it from the beginning. We are running the query. What was the query? Text search for. I gave it a text. User code. Where is the user query, guys? Yeah. Do you see this user query? Can somebody tell me what is the user query? A friendship with animals. And here, just to make it easy to understand, I've made it into a table. In this, the table didn't render as well. I should have made it wider. This is the similarity score. And it came back with the author and the category, the last two columns. Where are the last two columns coming from? Exactly. And where is the quote? Quote, these are the best quote. Would you agree? Look at the sentence. Animals are such agreeable friends. They ask no questions. They pass no criticisms, is the text. The other one is, the best thing about animals is that they don't talk much. Now, you would agree that these results look relevant, isn't it? Now, look at that. What is the prompt that we gave? You're an expert assistant specializing in animal wisdom. You have access to a curated list, blah, blah, blah. Your knowledge base. You work with search results containing animal code. Each search results includes quote content, author, category, similarity score. Your capabilities. What is it? I gave a very simple instruction prompt. In reality, it is more complex than this. So this speaks to the fact that in real RAG system, your instruction prompt, your prompt has to be very well done. Right? I'm just giving you a touch of reality here. This is how you would craft it. Response guidelines, be conversational, use blah, explain relevance, example response, etc. Content format, usage instruction, etc., etc. Quote. Use of a friendship with animals. Quote. Animals are such agreeable friends, they ask no question. Similarity score is this, etc., etc. Then this RAG example complete. Let's look at the next example. Okay, this thing is repeating itself. We'll leave it. Now what I want to show, I think we have more examples. So guys, are you getting the hang of it? The broad hang of it. How would you go about looking at it? Look into the animals class, and actually Why do I have examples in two places? I think I may have done a bit of mischief here. I have an example here in SRC usage, and I have an example here. Let's run both, see what happens. Maybe it's the same thing, but just to be sure. Yes, it's the same. I think I've accidentally put it. Then uh, we will do something more interesting. Let's look at it a little bit more visually. And are you guys up to some fun? Let's show you something. Let's open another tab. By the way, are you guys having fun? Is it proving useful? It's still building something up. Let's see what it cooks up. How many of you are familiar with MK Docs? It is just a way for you to, okay, I could do slightly differently. If you're not, if too few people are familiar with MK Docs, then I'll run it through. All right. How many of you are familiar with Jupyter notebooks? Almost all of you. So we'll take the Jupyter notebooks route. I'll take a very simple corpus. I took a corpus of, I believe, 16 documents. Very, very different documents. This is, for many people, their favorite poem, Jabberwocky. The defining quality of this bit of text is, if you read it, it seems to make sense. "'Twas brillig in the slithy toes, did gyre and gimble in the wave. All mimsy were the burgos, and the mom rats outgrape." You notice something about it? There's not a word in here that's in the dictionary. Right? How many of you know what brillig means? Or gyre and gimble mean? It's all very nonsensical. And yet it seems to make sense if you hear it loud. We'll keep it as an example. Another is a quote from a book called The Tale of Two Cities. It's a famous beginning call. "It was the best of times, it was the worst of times." Right? Another is a wonderful fact to reflect upon from Dickens. Another is again from Dickens. Then one is from Mark Twain about dogs. "A dog is a gentleman. I hope to go to his heaven, not man's." Einstein, "Tweedledee and Tweedledum" from Alice. Some things about golden retrievers, some things about dogs, Keats. And "Attention is all you need." Yesterday we talked about that, the abstract of that paper, and some explanation of backdrop, some Wordsworth's poetry, some other poetry. So I hope you're seeing a variety of documents, isn't it? Pretty varied documents. We will treat this as the corpus, and we'll go back and see what search means. Yeah. So what do we mean? See, guys, when you do keyword search, you realize it's unnatural. It is like me just using the word keys, keys. Yeah? And my family is totally baffled. What is it that I'm looking for? But ideally, we want to be able to articulate what we are looking for, right? The beauty of AI search, semantic searches, you can semantically express what you're looking for. The machine will magically figure out the right documents and give it to you. We talked about this magic, how it happens. It goes into vector databases, a nearest neighbor search. This is all, by the way, this is all part of the RAG GitHub, right? So you'll get it. Does this all now make sense to you? Right. So what is a, when you take a piece of text, let's say I took the first piece of text in the corpus and I converted it to embeddings, we understand English. The machine came up with this vector tensor. How many of you can read this tensor and say, aha, it is the Jabberwocky poem? Raise your hand. You can? Can you look at these numbers and say it's the Jabberwocky poem? No, you can't, right? So there's an interesting irony in here, actually. We have trained the machines to understand our language, but human beings have no ability to speak machinese. Right? You're looking at machinese, isn't it? And we have no idea what it means just by staring at it. It's an interesting asymmetry of our times. Machines understand us. We don't understand it. Quite an irony here. So what is the first thing you would do? You would convert all of these, use an embedder to convert all of it into vectors. Right? And so, and when you get a query, that also you will convert it to vectors. Let's see, where did I convert everything into vectors? I took a sentence transformer to embed. So embeddings are what? It's another name for vectors. I have embeddings. Now when a query comes, what do I need to do? The query itself needs to become a vector. Do I do that there? Let's see. I gave the query a friendship with animals. Right? So you use the embedder to create it into a query vector. I should have said query vector. And then what do? I go and compare it to the embeddings and find the top 3 nearest neighbors. And let's see what they come out to be. I get pretty good similarity scores, and let's look at those scores. And this is where, unless you pay attention, unless you pay attention, you would miss something pretty deep and remarkable here. What are the keywords present in a friendship with animals? A friendship in animals. So if you were doing a simple keyword-based traditional database search, the results, the top results would contain those keywords, isn't it? They'll be populated with those keywords. But look at the first result. The first result says, golden retrievers are not bred to be guard dogs. And considering the size of their hearts and their irrepressible joy in life, they are less likely to bite than to bark, less likely to bark than to lick a hand in greeting. In spite of their size, they think they are lap dogs. And in spite of their being dogs, they think they're also human, and nearly every human they meet is just to have the potential to be a boon companion who might at any moment cry, let's go, and lead them on a great adventure. What is conspicuous by its absence? The keywords. Nowhere in this long text it is there at all. Look at the second search result. If you are lucky, a golden retriever will come into your life, steal your heart, and change everything. How many of you have golden retrievers? Well, you don't seem to be very lucky. How many of you have dogs? What of you? Okay. Right? You'll soon realize that I love golden retrievers. Anyway, but look at the third search result. If a man aspires towards a righteous life, his first act of abstinence is from injury to animals. At least one keyword showed up, right? And it was the third result. And yet, would you agree? Look at this. I actually gave a very hard query. It didn't look like that. A friendship with animals is a what? Is it a thing? Am I asking it to search for a mug? I'm asking it to search for something abstract, an emotion, right? A friendship towards animals is an emotion. Can you imagine something that is capable of looking for texts that match that emotion? So, when you read the first search result, would you agree that the entire text expresses an emotion that the writer felt? And that emotion, the whole text reflects a friendship towards animals. It couldn't possibly be written by a person who doesn't love animals. Would you agree? Metrics. Yes, yes. Yes, yes. That's what the whole course is about. Everything is measured. Lord Kevin said, right? If you can't measure it, it's not science. Everything is precisely. That's the whole metrics and quantitative evaluation of every piece. Just like a car, you have to have a way of knowing how good this brake is, right? How good this engine is, and there are quantitative measures for each piece. For each piece of rag, there are quantitative measures of their own. And one of the mistakes, the most common failure mode in rag systems that people design is they build it as a black box, they feed it a few queries, they look at the response. Hey, the results look good, man. Let's release it. Right? That's the typical uh, attitude. It doesn't work like that. It's like, one second. It's like making a bullock cart and then saying, wow, it feels like a rocket. It doesn't. It's not in reality. Because what's the difference between, let's say, a very fast car and a bullock cart? They both take you from here to there. But it's the numbers, how fast it can go. No, they don't. It has very abstract. So when we talk yesterday, when I said, right, think of size, etc. But no, actually, embedders, they don't think like us. When they think about a text, they think very differently from human beings. Their machines in which they think are just points on a sphere, hypersphere. And their axis, like if you look at each of the dimensions, you and I would say, to me, it makes sense that one dimension should be size, another should be color, attributes. But actually, they are not. They are very abstract dimensions. To us, they look abstract. We scratch our head and saying, what is this dimension? Very, very hard to put our interpretations on its dimensions, its axes. That's a reality too. Yeah, 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 yeah. Nuance view. Yes. So, so it's a very deep question actually that you ask. What happens? Can I use interchange embedders in the same vector database? Oh, for heaven's sake, don't do that. Right? It's a catastrophe. One collection or one vector DB instance, use one embedder because another embedder will think differently. Right? Now there is so what have I said? Each embedder thinks its own way and stores points in its own way. That's a reality. The more mathematical way of saying it is that the geometry that each embedder uses is the embedders. Another embedder will throw points using into a completely different geometry, reality. Having said that, there is something called the Platonic hypothesis. Unproven. It's a hypothesis. The Platonic hypothesis in our field says that at the end of the day, all good embedders create equivalent geometries or equivalent representations. Not the same, but there is a way to do a equivalence morphism from this embedding to this embedding. From practical terms, it just means you're screwed. For, for deeper theoretical sense, it better be Platonic hypothesis better be true. Because I may speak, let's say that one machine is speaking, or human beings, we understand it in Mandarin, we understand it in English, we understand it in Tamil. All three understandings have to carry the same semantic burden, isn't it? And so there has to be an equivalence, a way to morph from your to mine and from mine to this. In other words, one should be able to cook up encoders that transform back and forth, right? That is all that you can say. No, that's not the way you think. The way you think, now I know where you're coming from, but in our field, what we say is, when I use a general embedder, the geometry that it comes up with is suboptimal. The way it throws points in the hypersphere is suboptimal for my use case. Therefore, and a lot of, see, directionally you're right. In a way, you're saying many axes are wasted, dimensions are wasted. Something similar happens, not that, but directionally you're right. But what happens is, you say the geometry that it creates is for a wide variety of text. I work in, let's say, finance, or I work in pharma. Mine is a specific domain. I needed to use a geometry that is optimized for my domain, right? That should use all the axes, all the dimensions, as much as possible for my domain. So what do? That is what you learn. When I said that you need to always take a general embedder from the internet, whatever is good one, then a necessary thing that you must do, otherwise it's a vast lost opportunity. You must reshape the embedder's geometry through fine tuning, right? And that fine tuning is essential. You must do. If I were to look at the most people's implementation of RAG, they all, I mean, it is like a, most RAG implementations is, it's hard to tell which mistake has remained uncommitted, right? It's, like if you look at typical RAG implement, I say that as a person who has gone and reviewed people's companies and advised companies. So it's not because they are fools. It's just that people are told RAG is easy. You'll pick it up. Just pick up this library, just use this, you're done. And so they're not thinking foundationally, because when you start thinking foundationally, like we are doing now, you realize the question that you asked. Directionally, you were right. A general purpose embedder may not be using my application, my domains, maybe not tuned to my domain. I need to tune it to my domain. Why did I not think about it before? How many people think about it? Surprisingly few. Yeah. What they do is, there is a leaderboard called the MTab leaderboard, where there is a ranking of the best embedders. They always go pluck the best embedder and use it. Whereas what I'm saying is, the best embedder, general purpose embedder, is a starting point for you. Then fine tune from there. All right, guys. So guys, I don't know. See, when you learn and come into this field, this is the nuances I'm saying. Sometimes that which is revolutionary, you miss, but you're looking at a revolution. Can you imagine a keyword search engine doing this? Ever? No, right? And that's the revolution. It is things like this that caused in 2018 for the whole search industry, the big guys, Google, Bing, to just make complete turn, right? and say, this is the new standard. Are we together? And right around that time, you must have seen a significant improvement in search results. So let's go further. Can I do visual search? Who says documents must be text? Right? So I'm taking this corpus and I'm showing it a dog. Now an embedder will convert this into a vector and search. And when it does that, look at the results that it comes up with. See, what is the input to the embedder? It is just array of floating point numbers, pixels. RGB channels are what? Just numbers. It is not seeing a dog, is it? It is just seeing 3 grids of numbers, right? Red channel, green channel, blue channel, RGBs of just floating point numbers. And it looks at that number and says, okay, let me convert it to machinese. It does that, and it has understood what it is looking at. And where is the evidence that it has understood? Look at the search results it comes up with. Would you agree? Would you agree that these are the perfect search results, guys? Right? So just think about it. What just happened? You just did multimodal search, multimodal semantic search. Completely beyond the scope of keyword search. So it is not even that you can compare. There is no comparison. There is nothing to compare to at this moment. Would you agree? There's not even anything to compare to. You have gone way beyond that. Could you do the opposite? Could you search for a text? Could you search with a text and through a large database of images and get some images? Right? So what we did is here, and that's why the reason that your database, when you clone this repository, unfortunately it's big because we have thrown in 25,000 images there. 25,000 is a large number. This is it comes from Unsplash. This data set is what they put in the public domain for research purposes. So guys, yeah, so there may be a licensing. Don't use it for corporate uses. So long as you use it for research and training, it's okay. Right? You cannot ship it with your product. Don't accidentally ship it with a product. Then you might have licensing issues. According to Unsplash, their license doesn't. What we do is, first thing we index all of those images. What does that mean? Every image becomes a vector, goes into the vector DB. Let's do that. Then we'll search these images. Let's take a prompt. What was the query? To love a dog, right? Oh my God. Do you see, I'm giving it hard prompts. To love a dog is again an emotion. I'm searching for an emotion now in images. A keyword search in which you had metadata introduced, this picture has dog, this picture has person, still wouldn't capture the emotion. Look at this. Would you agree that this result is a resounding validation of the power of semantic search, of AI search? Would you agree that nothing further needs to be said when you look at this image? It is to love a dog, right? No, not generated. These are original. These are Unsplash. This is one of the largest repositories of images that are available for public consumption. No, you pass it through the embedder, no? What was that? Yes, that is it. You're not doing LLM. Yeah. It's not a full RAG system. It's only the search. So I'm just showing you the power of search, right? A retrieval system in this particular Jupyter notebook. But would you agree? Do you see where the power of RAG comes from? A lot of the power comes right from the first piece. There are 2 pieces. I'm showing you the power of the first piece first. Later on, see, we all know the power of LLMs. Not many people have appreciated how much power there is in the retrieval part of it itself. And I'm trying to make you aware of that. What about this picture? When you look at this, what do you think? What about this? Right? You almost feel like being that dog. Right? Oh, what about this? Does it capture very precise? See, we are not showing pictures of dogs, which would have been much easier. Do you see the precision of understanding that these AI language models bring? They truly understand what that phrase to love a dog means. And they truly understand what this image is saying, right? It is not just breaking it up into parts, dog, shoulder of person. It is going deeper, right? That's the power that you should be aware of. Likewise, look at all of these images. Do I need to go further? Then another prompt. By the way, when you do this, right, this Jupyter notebook, play with it, guys. Give your own prompts. Change it to whatever you want. Right. Now I ask for something that looks deceptively simple, a house near a lake. Now, there are two layers of meaning in a house near a lake. House near a lake is literal, a house near a lake. But the house near a lake could be some industrial building next to a lake with graffiti on it or whatnot. Right? But when people talk of house near a lake, what is the feeling that it evokes? We all want to have run away from the madding crowd, from the corporate, from the cities, and have a beautiful house next to a lake, a solitary house. How many of you dream of that? As soon as your startup goes IPO, that's what we'll do: buy a house next to a lake, and that house will obviously not have too many neighbors next to it, and it won't be in an industrial area. Look at the picture. Does it convey that sense of solitude, idyllic solitude, in the images? In that corpus, there are other images of house next to a lake. But this, look at these images that it picked up. What about this? If there is one quality common to all of these pictures, it is that quality of solitude, right? And peace. So it captured not only the literal meaning, but the rooting that humans have when they talk of house next to a lake. Right? This is it. Look at this. All of these. Then the next one was jumping dogs. Jumping dog. Ah, action. This time you asked for action and you got action. Would you agree? Right. Let's go down to another one. This is a little interesting. Pathways through the forest. When you say pathway through the forest, would you agree that these are very pertinent images? But this image caught me by surprise. Actually, I had to stare at it for quite some time to realize that it was the aerial view of pathway through a forest, snowed up forest. Right? And still it got it. And you could say, you could of course ask for more obvious things. You could give it a car image and say, go search for cars. And it would come up with images of cars. Again, so it's an image to image search at this moment. So when I was doing this last time, I was telling people to pick a word. So I asked them to pick hard examples. One example they picked was serenity. Now, serenity, how many of you have seen a picture of serenity? It's hard, right? And yet, look at the pictures that it picked. Would you agree that they convey a sense of serenity? So, guys, go play with all of this and enjoy. I hope you saw something fun happening. Would you agree? Right? And that is the field, guys. It's a beautiful field that's capable of amazing things if you build your systems well. I've given you this code. We'll be happy to give you help on the code. All the usual Bs, there are different vector databases, there are errors, there are factory to choose which type it is. Then Let's see if any part is hard to understand here. Oh, this is the vector DB, not this. Vector. Yeah. So where are these Jupyter notebooks? They are in the examples, docs examples directory. Are we together, guys? They are in the docs examples directory. And one more thing I must tell you, to make it easy for you to navigate this code base, we have given you a copy. Let me give you this. Uh, 1 second. Those of you who are not familiar with MKDocs, it is worth mentioning that you should look at. No, that didn't help. What just happened? Back to the chart. Let me copy this. And we're almost done, guys. I'll be happy to talk about more of this, but yeah. So the entire code base is well documented. I would suggest that you start with the MKDocs. It will give you all the architecture diagrams of what is where, right? So what are the two interfaces, guys? User query goes in, you get results. RAG component, semantic search you just saw, vector database, text embedder, image embedder, data models, animal corpus is the collection of documents. Right? This is the structure of the code. This is how you would use it. Is this useful, guys? You can play with this. Examples are here. Right? And all the examples are documented. Right? You can go play with it. API docs are here. Right? It's a very easy way to navigate through the code base. Please help yourself with it. Oops, what just happened? Yeah, navigate through this. Let me know what else can I show you guys. Oh, one more thing I wanted to show is how should the results come? RAG context, generate one step animal filtered content. So when you do this, one of the things you will realize is the return value of the animals RAG class. Let's go and look at that. And that's the last thing I'll do, and then we can all call it a day. Where am I? RAG. It returns a dictionary of what? If you look at it carefully, when it returns, see what all things it returns. It returns the result, the LLM response. We always think of the answer as the LLM response. But why will you trust the LLM response? It is always a good idea to also return the search results. Does that make sense, guys? So user can validate whether it's true or not. Then, not here, but later on you'll learn that we ask you to find why, like ground each sentence in the response with references. So in other words, I will show it not here because that is part of the full course, but I'll show it how good RAG is done. Suppose you go to Perplexity and let us ask it a question. What I'll ask it what are something very arcane. Observe how a good RAG system responds. It gives you an answer, doesn't it? But do you notice that every answer is grounded with sources? Yes, source. Do you notice that you can't move further without seeing the grounding? Right? Did we talk about grounding? Why? Because they have validated that they are not hallucinating, right? So what are the things that it will prevent? It will prevent the kind of problems, for example, sending traffic to your competitor's product, right? Or saying something outright wrong. The other thing that is very helpful is to give related questions. Whenever you respond in a good RAG system, see, a question is part of a conversation. So what should a good RAG system do? It should lead you on to the next questions, follow-up questions. So it should always say, what are good follow-up questions, right? Now, user may choose those follow-up questions or it may not. And here are the sources that it gives. So I'll end with that. I'll take questions. I hope this code walkthrough or this thing gave you some sense of how RAG works. Was it useful? You guys were very quiet. Okay. All right, guys. So I hope the purpose of this was to instill some appreciation of how RAG is done and how it's a beautiful subject. It's a whole new field. Right? Okay, guys. Questions? When you index it. In the indexing part, in the vector DB, let's go look at the code. RAG to riches. In the RAG to riches, in the embedder, let's go to the embedder. If you look at the embed vector DB, right? First thing is, look at the embedder. In the embedder, what are we doing? There's an embed method, content, and metadata. Metadata is a dictionary. So what can I do? In the dictionary, I can say author, blah, category, blah. And when I create embeddings and give it to the database, vector DB, I can give that dictionary. Make sense? That's it. All of these are easy, but when you first come to it, it looks like a little bit overwhelming. That is why start with the documentation, the MK docs, because there is a careful walkthrough of each piece and explanation of it. Yes. C, the answer to that is yes. If you give it exactly the same text and the same text again, you'll get exactly the same. But if you vary the text, you will not get exactly the same. And theoretically, yes, you can get. Theoretically, two different pieces of text, if they are semantically the same, they can produce the same embedding. In practice, we know it doesn't do that, and there's a simple reason for it. Imagine 2 points which are very close. How many points exist between them? No matter how close 2 points are, there are infinitely many points in between them. So there are many, many shades possible even between those nuances, isn't it? So it doesn't happen. In fact, there's a recent remarkable uh, uh, paper that shows that. It says that theoretically it is possible that it's a lossy thing. These things could, two different texts could be mapped to the same point. In practice, it never happens, right? In fact, it's an injective transformation. I think, are you guys all strongly hinting I should end? Go ahead. See, there are systems that do joint embedding. What you will have to do is, it will go through a text embedder, it will go through an image, a joint, like an embedder which can do both, and then you concatenate the embedding of both of them, right? And you can either take the concatenated embedding as one giant vector, or you further transform it with another matrix or something and get a vector. So there is a whole field called joint embedding. In fact, If you just look at one of the most remarkable papers that recently came out is about joint embedding, right? Retained architect. JEPA is a big area. But JEPA is used in many places. SAM, segment anything models use joint embedding. Many things are there which use joint embedding. You can keep it in the same database, or you can keep it in separate databases. Absolutely. In fact, think about it this way. When you look at a technical textbook page, a technical report or something like that, in the same page, you will find text, you will find a chart, a plot, a graph, you will find an image of a machine, let's say, right? Or something, diagram, neural network diagram. What is there? Text is there, a chart is there, actual image is there, and while we are at it, let's throw in a table also. A table of some data is there. The point is that's what makes RAG interesting. You see that? Eh? Can you imagine that modern RAG systems actually understand that page in spite of its complexity? No, it returns the answer spanning all of them. It remember what does a RAG response return? Text answer. So it will return an answer, right? So for example, let's say that in one page there is a graph that shows that, let's take something. As the temperature increases of a gas, the pressure increases. And it is there as a chart. Let's say that in that page that sentence is not written. There's just a chart there. What do you think RAG will do? RAG will say, and you ask the question, are temperature and pressure related? RAG will say, yes, very much so. The pressure of a gas is directly proportional to its temperature, right? And as evidence, it may pull up that page. Right? But the beautiful thing is, it understood that graph even though there were no words written there. That's the power of AI. See, in a way, right, to really become great at RAG, and as I said yesterday, most people are not. See, you stop learning the day you think you know it already. The problem that has happened with RAG is that people think it's a bunch of libraries that you can use. The reality is RAG is a vast and deep area of research and massive practical applications. Every single large-scale generative AI that you see is actually RAG. ChatGPT is RAG, agentic RAG. Perplexity is, Gemini is, Cloud is. Your coding agents. How many of you use Cloud Code, etc.? Cursor, Cursor, right, etc. Copilots. All of them are RAG, but they are not done. But to build that kind of RAG, you need to understand its power. You need to understand how to harness that power. It's all there. Does that answer your question? Okay. So guys, again, forgive me to remind you, give me 2 minutes of marketing and then you guys can go home. We are Support Vectors, supportvectors.ai. If you go to schedule, we are coming up with a whole list of new courses, boot camps. They are fun. Anybody can vouch for that? Okay, many of you. Okay. So then, in particular, we are starting with this course, enterprise. I mean, if you're interested in RAG, you can take the enterprise RAG course, which is, where is it? It is this course. It has labs, lectures, quizzes, projects, research papers. There are 10 teaching assistants to help you. It's a very instructor heavy course. These are all the topics. It is taught by me and my friend, and partner here, uh, Chandra Lakshmi Narayan. He is also from IIT. He's from IIT Chennai, one of the top rank holders, and a US PhD. Right? There are lots of other TAs. You can do that. Did I not have um, a coupon? There is a coupon that I can point you to. Okay, let's maximize that. Today, and I suppose for the next week or so, if you guys register for the Enterprise Rack course, if it interests you, my team has told me to inform all of you there's a coupon, $100. So now might be a good time to talk to your boss and get permission to take this course. With that, I would end the formal session. Any more questions, guys? All right, guys. So many thanks for coming to this meetup. I I know you come from a whole day's work and you must be very, very tired. Sushan? Oh, that is a very good question. Actually, we have a whole data center. So one of the things you get with the course is genuine hardware. You won't be doing your lab on the laptops. You'll be doing it on a cluster, which is a $500,000 cluster. You're doing it on Blackwells, right? And these GPUs are expensive. They're $8,000 GPUs each, right? And we have banks of them. You get a full unrestricted access to extremely powerful hardware. So you will be doing, see, when we say that you do enterprise class projects, we mean it. You don't do toy projects. You do real projects on real hardware as a team, and what you build quite likely will either help you, like in the past batch, people came who knew RAG and they used what they learned here to make a substantial difference to their internal projects and work. They were leaders, and a couple of startups came out of it from the projects they built. So you will be doing very realistic projects in the enterprise. The 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 other side of it, of course, is that these are intense boot camp. 3-month boot camp. You bring in the effort, you will walk away with more learning and results than you can imagine in 3 months. All right, guys. Thank you for asking that question. Anyone else, guys? Okay. So we'll end that. Samantha, let's end.